Okay, Assalamualaikum warahmatullahi taala wabarakatuh. Dan selamat petang semua. Alright, so today we're going to talk about the chapter 2, step number 4, which is we try to determine the solution of the system, of the equation, or the response of the systems. Step number 4. Step number 1, there are two main steps that you need to know, which is you need to know the configuration of the system, which is the positive direction or the effective direction, or the positive coordinate system, and where is the equilibrium position of the system in order for you to sketch the free body diagram, right? And then after that, you look at the system, whether it is a rotational system or translational system. If it is a rotational, you use Newton's law for rotational system. If it is a translational system, you use Newton's law for translational systems. Or if it is a combination system, especially dependent motion, I advise you to use the rotational Newton's law. All right. And then after that, use step 1 and step 2 to get equation of motion. We have done that. Okay, for today, we're going to look at step number 4 here, which is we're going to look at the response of the system or the solution of the equation. Okay. All right. And then there are a few cases that we are interested in chapter 2, which is translational system, as I mentioned it before. Either it is moving in horizontal motion or vertical motion, or we have rotational systems, which is whether it is rotating clockwise direction or it rotates anti-clockwise direction, or you have a rotating without slipping, or you have a combination system, which is dependent motion for single degree of freedom system. All right. And then today we're going to discuss another case, another system which is a stability condition like this one. I will discuss it later. All right then. So let's look at the step number 4. Step number 1, we sketch the free body diagram. Step number 2, we select the Newton's law according to the motion of the system. Step number 3, we apply 1 and 2. Step number 4. So what is step number 4? Step number 4 is basically we try to get the response of the equation. The response of the system. How the system will respond to the under free condition, under free vibration. Or we can say that we try to determine the solution of the equation. Since our equation of motion is ODE, ordinary differential equation, okay? So we try to get the solution for ODE. Mathematically, to get the solution for ODE, we can represent it using the complementary solution plus particular solution, okay? But in our case, for chapter 2, particular solution will be equal to 0. I put it here. The particular solution is going to be equal to 0. Why particular solution is equal to 0? If you still remember, our equation is in the form of mx double dot plus m equivalent x double dot c equivalent x dot plus k equivalent x is equal to 0. So our equation is equal to 0, means that we have the linear homogeneous equation. Okay, so there's no terms on the right hand side. If we deal with the force vibration chapter 3, we will have the particular solution. So for chapter 3, we will have both complementary solution and particular solution. But for chapter 2, the particular solution is going to be equal to 0. Since the terms on the right hand side is equal to 0, so there is no force in the system, so particular solution is going to be equal to 0. The one that we have here is the complementary, or in layman terms, our solution will reduce with time. If you look at the undamped system, all the response will be diminished with time, except the undamped system. Okay, so complementary will cover for chapter 2. Complementary plus particular will cover in chapter 3. All right. So after this, I will not write as complementary anymore. I will write it as xt. I will write it as xt. All right. Okay. So in order for us to get the response for free vibration systems, we should derive the roots of the equation. What is the roots? For example, like you learned in mathematics, you have learned in mathematics about quadratic equation, x squared plus x no x, and then you get what is x1, what is x2. So it is similar here. In our case, we have ODE, which we have ordinary differential equation second order, which is x double dot, x dot, and there is no dot for the final x. Okay, so if we get the roots of this equation, we will have two roots. One roots we can represent it as S1, and another one we can represent it as S2. Okay, so we should derive, you should derive this one at home. Okay, I put the answer here. So if you derive the roots of the equation, you will get this answer. That is the roots of the equation in terms of C, M, and K. Or we can represent this root in terms of zeta and omega, and this is similar but different representation. Okay, so how to derive this one? We should expect, or we should predict the response in terms of A exponential ST, substitute into the equation, and then rearrange it, and then finally you get this root. Okay, so you should do it at home. Okay, so once you get the roots, you should have two type of response here. One, if your roots is similar, this one. Another one is if your roots is not similar. Okay, so I put it here. If it is a critically damped case, you will have one equation. This equation here will be used for critically damped case only. And this equation here will be used for three cases. One is underdamped, second one is overdamped, and the third one is undamped. So what are these three cases, or these four cases? These cases depend on the zeta. I put it here. If zeta is equal to 0, means that there's no damping in the system, that is undamped. If zeta in between 0 to 1, that is underdamped. If zeta greater than 1, that is overdamped. If zeta is equal to 1, that is critically damped. Okay, so how to calculate the zeta value? I mentioned it last week. So once you have the equation of motion, you can determine the omega n, you can determine the zeta. So zeta, you can determine it using the equation, or you can compare it with the parametric equation. So once you know the zeta, you know on which equation you should use. Okay, so I summarize it here, 1 to 4. So for undamped case, if zeta is equal to 0, you should get these roots. How to get these roots? If zeta is equal to 0 here, zeta is equal to 0 here, this term is going to be equal to 0, this term 0, so the whole term here will be equal to square root of minus 1. So square root of minus 1 is equal to square root of minus 1 multiplied by square root 1. So square root of minus 1 is equal to I or J in complex number. So we can use J here as omega n in our answer. So plus minus, you have two different roots, plus J omega n minus J omega n. Okay, for the second case, if we substitute the roots here, we should get this one. Why I change these ones? Because I want to put J outside, so that's why 1 minus zeta square. And then these two cases, we have a real root, so we should maintain as it is. Okay, so let us go one by one. So for undamped case, if we substitute this root into, this is different roots, into this equation here, S1 and S2, okay, and then we derived it further, finally, you will have this equation. So this equation is the response equation, or the solution for our ODE, for undamped case. So you should know on how to use this equation. Don't remember this equation. This equation will be given in the exam or in the assessment. You just need to know on how to use this equation. So step number 4, for undamped, this is the important equation. Okay, or we can represent it in two different forms. Either we use sine or we use omega cosine. Okay, all right. So how to use this equation? A1 and A2 can be determined using initial condition. What is the initial condition? At time t is equal to 0, what is the value of x0? What is the value of x dot 0? Later on, I will show you one example for this one. All right. For the second case, underdamped case, this is the equation that you should know. Don't remember it. You just need to know on how to use this equation. Okay. So zeta, you can determine it from step number 3. Omega n, you can determine from step 3. A1 and A2, you can determine it using the initial condition at time t is equal to 0. Omega d here, omega D, we call it as damn natural frequency. We call it as damn natural frequencies. I write it here, damn natural frequency. Okay, so omega D. So damn natural frequency. Okay, so omega D is equal to omega n multiplied by cert 1 minus zeta squared. So once we have omega n and zeta, you can calculate omega D. So again, A1 and A2 determine it using the initial condition. Right? Then step number 3, this is the equation that you should know. Okay, don't remember it, but you need to know if you have the damping ratio greater than 1, this is the equation that you should select. And then how to use this equation, you need to determine A1 and A2. How to determine A1 and A2? Using the initial condition. What is S1? This is the roots for S1. Okay. And then step number 4, similar for step number 4, get the roots for critically damped case, and then substitute it into this response equation, and then you should get the answer for the response equation. I review back the steps. Step number 1, you should sketch the free body diagram, know the equilibrium position, know the configuration of the system, whereas the positive direction using the coordinate system given, or you can make your own assumption. The second step, select the Newton's law, the appropriate Newton's law, or if you want to use the energy method, select the appropriate energy equation. Okay, and then step number 3, use step 1 and step 2, then you get the equation of motion. So in step 3, we can determine omega n, we can determine the zeta. Once you determine zeta, you look at the zeta value. If zeta is equal to 0, no damping, you use this equation. If zeta less than 1, greater than 0, you use this equation. If zeta greater than 1, you use this equation. If zeta equal to 1, you use this equation. That is a step for step number 2, for chapter 2. Okay, so we left with one topic, which is logarithmic decrement. Okay, alright. So any question? So there's one thing yang saya nak mention. Before this, saya rasa mungkin saya dah sebut. I've mentioned this before. So how we should draw, or we should sketch the forces in the FBD. So if let's say we have a system here. Okay, we have a system here. Okay. Alright. So in this system, we don't know whether this block M moving to the right or moving to the left. So we can make our own assumption here. So let's say we put the coordinate to the left as X, or we put the coordinate to the right as, saya pakai blue color, to the right as blue color X here. Either one. Okay. So I separate it into two sections here. So for the right color, if let's say we use the right color coordinate system, positive or to the left hand side here. Alright. So when this block moving to the left hand side, okay, what happened to the spring here? Spring we experience compression. So when this spring experience compression, when you draw this, or when you sketch the free body diagram, you should sketch the reaction of the spring. So when the spring in compression, it will react. So the reaction is basically in tension. Since the spring in compression, so it will react in tension. But for this case, when this block moving to the right, this spring will experience tension. So when the spring experience tension condition, you should draw the reaction of the spring in compression. So how we write the equation? So this is equal to Kx. So this one is also equal to Kx. Alright. So as I mentioned before, since this side we are not really interested to know because it is attached to the free end. This side we don't want to know. So you will have this one. So if we derive this one, this is x, that is x. So if we derive the one, we will have this one. Summation of forces is equal to MA to the left is positive. This one is summation of forces is equal to MA, to the right is positive. So you should have this one as minus KX is equal to MX double dot. Also here you have minus KX is equal to MX double dot. Then finally you have MX double dot plus KX is equal to 0. So this one also MX double dot plus KX is equal to 0. So it really doesn't matter how you select the coordinate systems, as long as you put or you apply the right reaction force on the spring. If the question gives you the coordinate system, just follow the coordinate system from the equation and then look at the spring condition, whether it is in tension or compression. And then after that, you apply the reaction of the spring in your FPD. We do it completely. Okay, so we call this one as stability condition. Okay, stability condition. So if you look at the system here, we have a rod here. Okay, at this equilibrium position, this rod is in stable condition. At this equilibrium position, this rod is stable condition. Means that this rod will not move to the left, will not move to the right. Okay, so what happened? This spring, these two springs here will not pre-stretch. There's no pre-stretch in these two springs. So there's no K delta. There is no initial displacement of the spring. There's no K delta. So if there's no K delta, our mg here, you will have mg here. Okay, you will have mg there. So that mg will not be cancelled out with the K delta in this case. So let's look at the systems. Let's look at the systems. Okay. So let's look at the system. So if let's say this system moving like this one, okay, it moving like this one. So we put here as our reference point O there. So we, okay, so I put the force here as red color. So you have two forces there. Okay, right, and then I have another one forces here. Oh, sorry. Okay, all right. So this is the angle theta. We use the blue black color. Okay, so this is the angle theta. Okay, so you have when, okay, so we can use two type of coordinate here. Either, oh sorry, either we use coordinate as usual, which is x over there, or we use theta coordinate here. Okay, so when this rod, let's say we give initial disturbance for this rod to the right, and then we let go. Okay, and then it will move. At this condition, at this instant of time, we will have this condition. So you have mg force here, and then you have, since the first spring here will be in compression, okay, then what will be the reaction of the spring? So it will be in tension. So we draw something like this in tension. So something like this, something like this in tension. And the second spring here will be in tension. So we draw this spring in compression. Okay, so it's something like this. Okay, so we have two forces there. Then, as I mentioned, I don't want to know about this one. I don't want to know about this one. So what we should have here, we should have either we write it as kx, we write it as kx, or I use different color, or we can write it as k multiplied by L, the distance, the perpendicular distance here. Okay, so this is the distance. Okay, let me write this one. K multiplied by L theta. This is also, we can write it as k multiplied by L theta. If we want to use the theta coordinate system, we use k multiplied by L theta. If we want to use the x coordinate system, we use x k multiplied by x. So if you look at this triangle here, okay, this triangle here, okay, So let's say this is our x. So this is L, this is theta. So in order for us to get this x, so S is equal to L sine theta, or this is also L, or L tangent theta. L tangent theta. Okay, so let's say I put this one as P. So what is P here? Is equal to L over 2 in the middle, L sine theta. Sorry, L over 2 sine theta, sorry. L over 2 sine theta is equal to L over 2 tangent theta. Okay? Alright, so that is the distance of L and P. So for small angle theta, if you still remember, for small angle theta, we have that sine theta is equal to tangent theta is equal to theta, and then cos theta is equal to 1. I derived it also. I mentioned this one in the class during the face-to-face class using the Euler angle. So you should have this one for small angle theta. Okay, so using this equation, we should have here x is equal to L theta, then this is equal to L theta, and then this is equal to sorry. So this is equal to L over 2 theta. This is also is equal to L over 2 theta. Okay, so that is how I get these two terms, KL theta and KL theta. All right. So now, from here, that is step number 1. This is step number 1. F, B, D. Okay. And then we go to step number 2, which is Newton's law. So in this case, this is a rotational system. So in this case, we know that for rotational systems, our Newton's law is summation of moments is equal to I theta double dot. Okay, but this moment we know that the whole rod will rotate about n axis passing through point O. So we know that the reference point here is point O, and it will rotate clockwise direction. And then step number 3, what we can do, we use step 1 and step 2. So we have 3 forces there. So I write as a complete equation first. So we have minus kx, okay, this one, multiplied by perpendicular distance. Since we do moment here, so remember we use moment equation. So force multiplied by perpendicular distance. So in this case, you can write as this perpendicular distance, So this distance is L cos theta, or L. So you can write as L cos theta, or later on I will show you, you can write it as L. So minus kx multiplied by L cos theta plus mg multiplied by L over 2 sin theta. Why plus? Because mg is going to be clockwise, kx will be counterclockwise. Mg multiplied by this distance, which is p in this case, this distance, p in this case. So p in this case is L over 2 sin theta, okay, and then is equal to I naught theta double dot. Or we can write it like this, minus kx multiplied by perpendicular distance is L minus kx multiplied by L plus mg multiplied by L over 2 theta. Okay, since you use this distance, this distance, okay, all right, and then is equal to I naught theta double dot, either one. Okay, so or we can change this x into KL theta. So you can use like this, so minus kx is equal to L theta multiplied by L minus KL theta multiplied by L plus dengan mg L over 2 theta is equal to I naught theta double dot. Then we can rearrange this equation as I naught theta double dot plus 2k L squared theta minus mgl over 2 theta is equal to 0. Okay, rearrange everything, you should get I naught theta double dot plus 2k L squared minus mgl over 2 theta is equal to 0. So this is what we call it our equation of motion, step number 3. Okay, step number 3. And normally we can write this one as m equivalent. We can write this one as k equivalent. Why k? Because this is theta. If you have a theta dot here, then that is c equivalent. Okay, so in order for us to determine the natural frequency, you use two ways. You use two ways to determine the natural frequency. You can use two ways. One way, we can use the equation straight way. Omega n is equal to such k equivalent divided by m equivalent. Okay, so what you should have here, k equivalent in this case is 2k L squared minus mgl divided by 2 and then divided by I naught. Okay, or we can compare it with the equation, parametric equation, which is x double dot plus 2 zeta omega n x dot plus omega n square x is equal to 0. So how to compare this one? Make sure the coefficient in front of the x double dot terms or variables is equal to 1. So our equation there, I should use the black color. Our equation there, we should represent it like this, plus 2k L squared minus mgl divided by 2 divided by I naught theta, okay, is equal to 0. Then we can compare this. Then we can compare this. Okay, there is no x dot term, so you cannot compare x dot with the theta dot. Okay, so we can compare the same coefficient, double dot with double dot, no dot with no dot. Okay, so in this case, when we compare this one, then we will know that omega n square is equal to will be equal to 2kl square minus mgl divided by 2 divided by I naught. Okay, so to get the omega n, we can use something like this. We cancel this one and then we put square root over here. Then you get omega n. So if you compare these two, it's similar. Okay, either one. If you remember the equation, you can use the equation, but make sure that you write it properly, which is m equivalent and k equivalent there, or you can compare it with the parametric equation. So in this case, our zeta is equal to 0 because there is no damping. Zeta is equal to 0. So if you compare 2 zeta omega n is equal to 0, so zeta must be equal to 0. Okay, so when zeta is equal to 0, step number 4 here, step number 4, when zeta is equal to 0, so this is undamped case, right? So for undamped case, then we look at the equation. Okay, for undamped case, okay, so for undamped case, we know that this is the equation that we should use. Okay, so for undamped case, we should use this equation. Xt is equal to A1 cos omega nt plus A2 sine omega nt. Okay, so that is the equation that we should use. Okay, so in order for us to get the A1 and A2, omega n, of course, we can determine it from this equation here. Okay, from this equation, omega n is, we can determine it from there. But A1 and A2, we need to know from the initial conditions. So normally at time t is equal to 0. So let's just put symbol. X naught is x at time 0 is equal to, we just put value, x dot at time 0 is equal to x dot naught. Okay, let's substitute here. Okay, so for time t is equal to 0, so x time t is equal to 0, that is equal to x naught, that is equal to A1 cos omega nt, omega n multiplied by 0, okay, plus A2 sine omega n multiplied by 0. So if we rearrange this one, you akan dapat, you will get this one. X0 is equal to cos omega n multiplied by 0, you get 0. And then cos 0 is equal to 1. So A1 multiplied by 1 plus sin omega n multiplied by 0, 0 sin 0 is 0. So that is equal to A2 multiplied by 0. So finally, you akan dapat that, A1 is equal to X0. Okay. So how to get A2? So we know that the velocity here is equal to x dot naught. So we should differentiate the equation once. So x dot t is equal to, we differentiate this equation once, is equal to A1 omega n sine omega n t minus, don't forget, because from cosine to sine you get minus, okay, plus A2 omega n cos omega n t. That is the equation. Okay, that is the equation. So let us substitute the initial condition. So x at time t is equal to 0, you get x dot 0, that is equal to minus A1 omega n sine omega n multiplied by 0 plus A2 omega n cos omega n multiplied by 0. So you get here x dot naught is equal to sine 0 is equal to 0. So that term is going to be equal to 0. So minus A1 omega n multiplied by 0 plus cosine 0 is equal to 1. So you get A2 omega n multiplied by 1. Okay, so you should have here A2 is equal to x dot naught divided by omega n. So you get both A1 and A2 in this case. So let's substitute it again. Xt is equal to A1 in this case is equal to x naught cos omega n t plus dengan x dot naught divided by omega n sine omega n t. Alright. If you have the values, substitute value omega n, substitute value x dot naught, then you should get the equation, a complete equation. So this is the response equation for the system. Step number 4. Then we can determine the velocity by differentiate this equation, and we can determine the acceleration by differentiate this equation further. That is step number 4. Okay, saya ulang lagi sekali for the mg. Saya ulang lagi sekali. Let's go here. For this one, at equilibrium position like here, okay, the mg will not pre-stretch the spring. Dia tak akan bagi initial deflection to the spring. So there is no pre-stretch in the spring. So there is no k delta. There is no static deflection. So mg will not be cancelled out with the static deflection. That's why in the equation you have mg. But for most of the cases, for example, like this beam, okay, for example, like this beam, okay, ada spring over here, okay, for example, like this one. So you ada mg over here. This weight akan bagi pre-stretch dekat spring sini. So mg ni dia akan ada k delta, over there. So in the final equation of motion, mg dengan k delta ni will be cancel out each other because this weight dia ada pre-stretch dekat sini. Dia bukan stable condition. At equilibrium dia ada pre-stretch dekat spring. Okay, if there's no pre-stretch dekat spring at equilibrium position like this one, then you will have mg. Okay, ada banyak lagi case. Contoh, if you gantung rod ni macam ni, if you gantung dia, okay, this rod you just hang it there, okay, and then you attach a spring to this rod. So at this equilibrium position, this spring will not be pre-stretched by the mass of the rod. So mg ni tetap ada. So bila dia moving here, mg akan ada. So spring akan ada kx ataupun kl theta. Okay, cuma dia tak ada k delta for this case. Alright, so bila tak ada k delta, mg akan ada lah. So for 2 degree of freedom system, kadang-kadang ada case yang macam ni, dia akan combine this one with this one, contoh, with this one, okay, with this one, for example, okay, fixed end, dia combine macam tu, okay, so nampak ada k, so ni ada rotating about O, for example. So remember when you derive for 2 degree of freedom system, yang ini okay, rotating about fixed point O kat sini, no problems, but for this one, you will have mg in the equation for this one. This is a stability punya case. So that's why I mentioned it before. For free body diagram, be careful, look at the configuration, look at the motion, look at the equilibrium position. If that it is in stable condition at equilibrium position, there is no pre-stretch in the spring, so mg will be there. It will not be cancelled out with the k delta. So hopefully dia answering your question. We will deal with mechanical systems. We have 3 element mass spring damper, so we will have 4 type of system, either undamped, underdamped, overdamped, and critically damped. So in order to solve this one, we follow the 4 steps that I put it as our guideline. So the first step is sketch free body diagram. So at this step, you need to see the configuration of the systems, whether it is at equilibrium position, whether it is in stable condition or not, there is a pre-stretch in the spring or not, and then you'll have to look at the positive direction, okay? And then step number 2, look at the motion, either it is translational or rotational, or combination of both, and then select the right Newton's law. And then step number 3, combine step 1 and step 2. And then step 4, step number 3, combine step 1 step 2 to get the equation of motion. From there, we can determine natural frequency using the equation, K equivalent divided by M equivalent, or we can compare it with a parametric equation, okay? And then we can determine the zeta value, all right? So once we get the zeta value, if zeta is equal to 0, that is undamped case, zeta less than 1 greater than 0, that is underdamped case, zeta equal to 1, critically damped case, zeta greater than 1, that is overdamped case. For all these 4 cases, you have their own their own solution for the equation of motion. Okay, so just need to select the right equation and then determine the A1 and A2 from the equilibrium from the initial condition, and then substitute all the values, and then you get the response equation. Okay.